Hi, chemistry students. This is your Unit 3 lesson on atomic anatomy, and we have lots of definitions. So you should be taking notes, very careful notes, as we go through this. Remember, you can speed up, you can slow down, you can pause, and you can stop as I go through these very important definitions that we're going to be using all year in chemistry. So I'm thinking that in previous science courses, in probably elementary school and middle school, you learned sort of the basic vocabulary of the atom. So I'd like you to pause the video and sketch this in your notes and sort of label these basic parts. Let me go through them. In the middle of an atom is something called a nucleus. A nucleus is very small and dense compared to the overall volume of the atom, and it consists of protons and neutrons. And those two particles make up the nucleus. Around the outside, making up and occupying a lot of the volume that is considered the atom, is something called the electron cloud. And in the electron cloud, electrons are found moving around the outside of the atom. Now, we often call these orbits, and in a later unit, we'll talk a little bit more about why that's really not a good picture. But they are more like bees swarming around a hive, but they do occupy, they're very, very small, but they occupy this much larger volume, and it's called the electron cloud. Now, protons, neutrons, and electrons are known as subatomic particles because they are smaller than an atom. They make up the atom. So you need to know this information. This might be a good time to pause the video and sketch to draw this table. But to go through it, subatomic particle of proton, we measure the mass of a proton, which is infinitesimally small, in something called an atomic mass unit. One atomic mass unit is actually equal to 1.66 times 10 to the negative 24th grams. Very tiny, not anything we can measure on a normal scale. But one proton has the value of one atomic mass unit. It has a charge on it, and the charge is a positive 1. So every proton carries a charge of positive 1, and its location is in the nucleus. The second subatomic particle is the neutron. It is about the same size as the proton. It is 1 AMU. However, it is electrically neutral. Every neutron has a charge of 0. It is also found in the nucleus. And the final subatomic particle is the electron. Now, when we're adding up the mass of the atom, we consider the electron to be an insignificant part of the mass. It actually is 0.0000544 atomic mass units. But whenever you're adding up the mass of an atom, you just consider that mass of the electrons to be 0. You don't count them when you're talking about mass. Now, even though they are very small, really small compared to protons and neutrons, they do carry a charge, but they are oppositely charged from the protons. They are negatively charged. So negative 1 for every electron. And they are found, as I showed you, in the electron cloud. All right, so we got two definitions for you. Okay, a definition for you that's very important. You're going to be getting very soon, if not already, a copy of the periodic table of elements. Periodic table of elements is arranged by something called the atomic number. You can see that if you go across, you have atomic number 1, then atomic number 2, and then atomic number 3, 4, 5, 6, 7, 8, 9, 10, and it's arranged by atomic number. Well, what is an atomic number? Now, all atoms of the same element always have the same number of protons. It's like their ID number. And the definition of the atomic number, which you can see is labeled right here, is the number of protons. The atomic number is the ID number of the element. So if you are presented with an atom in some way, and you're like, I don't know what this is, what's your ID number? And they say, well, my ID number is 6, because I have 6 protons in my nucleus, then you know the name of that element, the name of that atom is carbon. They are identified by the number of protons. If you have something that has atomic number 6, that has 6 protons, it can't be anything else other than carbon. Very important to understand. Protons are pretty stuck there in the nucleus. except in nuclear explosions, protons are not lost by any atoms. They are in the nucleus, and they allow you to say what the element is for that particular atom. So definition, atomic number equals number of protons. Okay, and move on. All right, now we need to talk about something called an ion. We talked about atoms in a previous unit. Atoms are always electrically neutral. So in an atom, in a regular old carbon atom, the protons are going to equal the number of electrons. In other words, when you add together, like in carbon, if you had 6 protons and it was an atom of carbon, you would have 6 electrons, and they would essentially cancel each other out. 6 positive charges, 6 negative charges. Okay, but there's something called an ion. And again, here's another definition. Ions are charged atoms. And there are 2 types of ions. There is a cation, and you'll notice there's a T in the middle of cation that sort of looks like a plus sign, all right? And in a cation, you have more protons than you do electrons. In other words, the atom has lost some electrons. We'll talk about that in later units. So you end up with a net positive charge, okay? An anion, and that's got an N for like negative in the middle, just like the T for the plus sign. There's an N for a negative sign. In this case, the atom has gained some electrons, so you have more electrons, more negative charges, and the overall charge of the ion is negative. So a cation is a positive ion that has more protons and has lost some of its electrons from its atom form. An anion is a negative ion. It has gained some electrons, and so therefore has more electrons than protons. Okay, so if you are given a problem, and I'm going to give you 2 in just a minute, to determine the charge on an atom or an ion, the charge is always essentially the protons plus the electrons, but since the electrons are negatively charged, we just subtract. Protons minus electrons will give you the charge and will tell you whether or not it is a cation or an anion. So here's the first example. A sodium ion has 11 protons and 10 electrons. What is the charge on the sodium ion? Is it a cation or an anion? Again, you're going to do charge, protons minus electrons, and let's look at the answer. You might want to pause it, write your answer down, see if you get it right. Make sure you're putting this in your notes. Okay, so a sodium ion has 11 protons and 10 electrons. What's its charge? The charge is the protons minus the electrons, or 11 minus 10, which means it has a charge of +1. We always put the charge on. Even if it's positive, you always still put the plus on it. So sodium is a cation. It's got a T in the middle. The capital T doesn't quite look like a plus, but T in the middle. It has more protons than electrons and a positive charge. So in other words, it has lost an electron to somebody. And again, we'll talk about that later on. Okay, here's the second one. A chloride ion has 17 protons and 18 electrons. What is its charge? Maybe pause, see if you can get it right. Okay, so the charge is protons minus electrons. This time it's 17 minus 18, so it's -1. It's an anion. It's somehow this chlorine ion, which has 17 protons, has somehow gained an electron from somewhere. We'll learn about that later. And it's an anion. It's negatively charged. It has fewer protons than electrons, and it's negatively charged. Okay, now we've got just a couple more definitions. There's something called a mass number. Okay, and you don't actually find this on the periodic table. We'll have a subsequent lesson when we'll talk about something called atomic mass. But a mass number is the number of protons plus the number of neutrons. If you recall, electrons are considered to have 0 mass, whereas protons and neutrons are considered to have a mass of 1. So just by adding up protons and neutrons, you find the mass of the atom. Okay? All right. So we need to define isotope. So you're going to write this down in your notes. All atoms of the same element have the same number of protons. And isotopes, the definition of isotopes, are atoms of the same element, so they have the same number of protons, that have different numbers of neutrons. And therefore will have different mass numbers. Okay? Because mass numbers, protons plus neutrons. So let me give you a couple examples. So what's in an isotope? here are some examples. So these are 3 forms of carbon, okay? So you can almost think of them as like twins, but they're in different shapes. One is more muscular and heavier, one is kind of medium, and one is kind of small. And it all has to do with the number of neutrons, okay? So we have something called carbon-12, carbon-13, and carbon-14. By far, the most common form of carbon is carbon-12. It is a carbon atom that has 6 protons, 6 neutrons, and 6 electrons. Again, mass number would be protons plus neutrons, and it would be 12, and so that would be carbon-12. Now, there are 2 what are called radioactive isotopes of carbon, and they're used oftentimes, carbon-14, in something called carbon dating that you might have heard about. But the difference is that they're just a little heavier. For some reason, when they're formed, there's 1 additional neutron in the nucleus for carbon-13 and 2 additional compared to carbon-12 for carbon-14. And you can see carbon-13 has 6 protons and 7 neutrons. Carbon-14 has 6 protons and 8 neutrons. Again, these are electrically neutral. So again, the charge, protons plus electrons, cancel each other out, 6 minus 6. But the difference between an isotope are the forms are slightly different. And when you go out in nature, and if you were to get a bunch of carbon, like some coal or some graphite or a diamond, those are all forms of carbon, and you were to look into them, you would see some of the carbon atoms would have 6 neutrons, a very, very few, but some would have 7 neutrons, and an even smaller amount, but definitely a countable amount, would have 8. So that's what an isotope is. So we write, in order to identify if we have a specific atom, which isotope it is. Okay, so this is just a specific atom. We have 2 ways we can write it. So carbon-12 and carbon, you saw on the last slide, carbon-12 and carbon-14, you can just do the symbol and then a dash and then the mass number. Or you will also see it written with the mass number being as a superscript and then the symbol. So these are 2 different ways of showing 2 of those isotopes of carbon. All right, another example, very important one, is uranium-238 versus uranium-235. You've probably heard of uranium, and you can see uranium-238 has more neutrons. Now, note, it's a uranium. Its ID number is 92. Its atomic number is 92. It's got 92 protons. Now, there's a big difference. There are some properties that are different between isotopes. Slight, but slightly different. Uranium-238 is very radioactive, but it can't be used in bombs. It's not what you call fissionable uranium, something that can be split and made to explode. It is the vast majority of the uranium. Now, it is still radioactive, and so if you're around it, you're going to get all sorts of radiation exposure, and it can kill you slowly because it's going to destroy your immune system. But uranium-235, which is a small percentage of uranium, actually can be used in bombs. And it's the fissionable type. And the reason why a lot of rogue nations aren't able to build bombs, there's plenty of uranium around, but you have to do something called enriching uranium, which means you have to increase in natural uranium the relative amount of uranium-235. So that means you have to do something with your humongous amount of uranium. You're going to have to try to separate out the uranium-238. They use sometimes these things called centrifuges to do it. But you have to get a massive amount of uranium in order to enrich it enough to get enough material to make a bomb that is mostly uranium-235. So there are some important differences in the isotopes. All right, so a few review questions. Test yourself. How are isotopes the same? How are isotopes different? Okay, so how are they the same? They have the same number of protons, and they have the same atomic number. They're the same element. Uranium-235, uranium-238, all 92 protons. How are they different? They have different numbers of neutrons, and therefore they have different mass numbers, okay? Different, apparently, is the way I spelled it here, but different numbers of mass numbers, or different mass numbers. All right, now, one other calculation you'll have to do is recognizing when you're given an isotope and you're given the atomic number and the mass number to figure out the number of neutrons. And it's just a subtraction. Remember, the mass number is just the protons plus the neutrons, and the atomic number is just the protons. So if you take the protons plus the neutrons, which is the mass number, and subtract the atomic number, protons, you'll get the number of neutrons. All right, a little bit of atomic notation here that you'll see. You will often see symbols of particular isotopes written in this way. So you'll have the mass number up here in the upper left. The atomic number will sometimes be down here in the lower left. And if there's a charge, it will appear up here on the upper right. So you can see the mass number is 4, the atomic number is 2. How would you figure out number of neutrons? You would just do a subtraction, 4 minus 2. It's nice how it lines up there. And then the electrical charge is 0. So that would tell us that the protons equal the electrons, 2 minus 2. And so therefore we would have to have 2 electrons. Let me show you another one. Here's a notation for a cation. All right, so this time you've got a mass number of 23, an atomic number of 11. The charge is a +1, and you put the symbol in the middle. Okay, atomic number is 11 protons. We can get that from the periodic table. The mass number is here, which is 23. Now, how do we figure out the number of neutrons? Well, we take the mass number minus the atomic number, 23 minus 11, and we get 12 neutrons. Note, protons and neutrons do not always equal each other, okay? And then the charge, well, we have 11 protons, and we have a +1 charge. So 11 minus what gives you +1? Well, that's 10, okay? So we must have 10 electrons. It's a cation. Makes sense. We have more protons, more positives than we do negatives. Now, I'm going to have you look at this, and you may want to, this is the last slide, and you may want to pause the video because homework I'm going to give you is going to be for you to fill in some charts like this. So this is a good example to study. Maybe you want to copy it, maybe you just want to study it, but let me just go through a couple of them. Make sure these all make sense. So we got lithium-7, you can see the notation. I have left off the atomic number. A lot of times you will see that. Where do you get the atomic number? From your periodic table. I've put the atomic numbers I got from the periodic table right here. Notice that the atomic number and the number of protons always matches. Okay? Now the mass number is easy. That is always in the symbol because it's a particular isotope. This represents just one lithium atom that is this particular isotope that has a mass number of 7, the sodium a mass number of 23, the sulfur a mass number of 32, and the chlorine a mass number of 37. So that's why this is the mass number. Okay. Now, we have to do a little bit of mechanation here. We've got 3 protons and 4 neutrons. And again, that's because protons plus neutrons have to equal the mass number. Okay. Now, what about the charge? Well, it's neutral. So if it's neutral, we know protons plus minus electrons has to equal 0. And we know it's an atom because it's neutral. Okay, we looked at sodium before, so let's look at sulfur. Okay, so we've got these 2 numbers from the periodic table and from the symbol for the isotope itself. We know that it has 16 protons, because this has to match. If we put a 16 here, 32 minus 16, we give us 16 neutrons. Now, how do we figure out the charge? Well, we know the charge is -2, and we know protons minus electrons has to equal -2. So 16 minus 18 gives us -2. How do we know it's an anion? Because it's a -2. All right, so that is your lesson on atomic anatomy and on these definitions that we need to be sure we know. Be sure that you have your notes handy when you do your homework, and thank you for your attention.